Good evening once again. It is your teacher Eugene. Now we are going to look about the power factor correction as the most crucial question used to meet when you are doing some installation of the induction motors or on inductive load. Most of the time it consumes high reactive power. We need to improve it by a power factor corrector tools, which is for our side today. You have to use a capacitor bank. Now let's begin with it. It is a three-phase 50 kilowatt induction motor. Now it is connected to a supply of 400 volts, 50 hertz, supply at a power factor of 0.5 lagging. Calculate the size of the capacitor to be connected, to be installed in a parallel to raise the power factor to 0.9 lagging. From what we have, as for our question, we have the load, the given one. We have the load that is the power, active power consumed, the load it is derived, it is 50 kilowatts. It is just connected to a voltage, this is a V line voltage, which is equal to 400 volts. We have the supply frequency for our side, that is a 0.7, which is lagging. But the desired power factor, EF, which is a desired one, it becomes 0.9 lagging. 0.9 lagging. What we need to know first of all the angle to which this power factor is corresponding with. Let's begin now. For cos, let's take theta 1, which is equal to 0.7. Now, theta 1 is equal to cosine minus 1 of 0.7. We use our calculator. Now, this is the cosine minus of 0.7. It gives 50.63 degree, and the cos theta 2, which is supposed to be small compared with the one, as if the power factor goes low, the angle between the voltage and the current goes high. So we need to look for this diminished one, that's 0. The cos which is 0.9. The theta 2, which is cosine minus 1 of 0.9. Again, it is equal to cosine minus 1 of 0.9, which is equal to 28.71. 28.71. We do it along, we took two numbers after decimal places. Now, from this one, we need first to know what is the amount of the current this load draws. Now, the current, remember the power will be equal to root 3 VL IL cosine theta. Where this is the current, the line current, the voltage, the line, the power factor. What you need to know, it is the line current, which will be the power divided by root 3 VN cosine theta. Now the line current will be equal to the power, it is 50 kilowatts, 10 power 3, divided by root 3 times 400 volts times 0.7, which is equal to 50,000 divided by root square root of 3 times 400 times to 103.09 amps. Now, for calculating the voltage capacitor bank, we just have the insert the capacitor that will consume some amount of current. For this line current will be equal to the current that the water consumes. Now, AL is equal to the current the motor it consumes. Let's use the phasor diagram for searching the current that a capacitor will be connected will consume. From the phasor diagram, now we have the current, this, we have an angle between, that is IM, for an angle of, let's call it theta 1. We need to supply, we need to add a capacitor bank which will consume IC to rise this current to a power factor corresponding to an angle of theta 2. Theta 2. Now, let's consider this point as O. And this is called, let's call this point V. Let's call this point A. A. Now, this amount of current when we just go to the active and the active, you remember that active we use the cosine, the active we use the sine. So this current will be equivalent to IC, and this one from here, this one will be equal to IM sine theta 1. And this one will be equal to I of C IC sine theta 2. When we are for active, the active always remain, which just means that always the current that is the magnitude of this current will never change as if the angle change. For active components, it means that I am cosine theta 1 will be equal to IC cosine theta 2. Now we have IM and the current amount is consumed. We have the power factor 1 and the power factor 2. Now the remaining is we can get the value of the IC. Sorry for nomenclature. That is the resulted current. That is I. That is IC. That is the current we are desired to reach after the power factor will be equal to I the motor is drugs cosine theta 1 over cosine theta 2. Then the current will be equal to IM from the previous is equal to 103.09 times 0 over 0.9, which is amps. The desired current will be equal to 103.09 times 0.7 divided by 0.9, which is equal to 80.18 amps. Now, from our phasor diagram, we continue for our question. We are going to search the IC. After getting IC, we proceed with our question. Now, let's keep our question and remind us as to calculate the power factor corrector going to be installed. Let's clean for getting enough space. When you look into reactive components, for reactive components, when we took, if you see IC plus the desired I sin theta 2 will be equal to IM sin theta 1. So, IC plus desired current sin theta 2 will be equal to IM sin theta 1. Now, for us, what is there before? It is the IC, which is equal to IM sin theta 1 minus I sin theta 2. Now, our IC will be equal to IM equal to 103.09 amps. Sin theta 1, it is 50.63 degree minus the result I have got 80 sin of 28.71 degree, which is half the unity of amps. Now IC will be equal to, let me take a calculator. The IC will be 103.09 sin 50.63, which is equal to 73.61 minus 80 sin 28.71, which is equal to 34.86. This is amps. Now IC, it will be 73.61 minus the answer will be equal to 38.74 amps. Now, what we got, it is the current that capacitor will consume. So, we are going to, if this capacitor, this four three-phase, this is the total current it is gonna consume. We're gonna search a per phase reactance to see what every phase will consume. That is the total current these three will consume. So we're gonna search per phase capacitor current will be current. Every phase will have the capacitor, but those capacitor, all of the three will consume at 8.74. Let's look per phase value. Remember, IC will be equal to V phase divided by XC, but this XC is perfect. Now, for this, just proceed to our question. Remember, XC is equal to 1 over CW, where this C, the capacitance, this is the angular velocity, and for our side, angular velocity, W will be equal to 2 pi F, where F is the frequency. Now, from IC will be equal to our IC will be equal to V phase times C times 2 pi F. Let's continue. IC divided by 3. This is for phase. Now we're going for phase. Will be equal to V phase times C times 2 pi F. And the C will be equal to now. Let's continue now for our question. Now that is we're going to set the value of C. That will be equal to IC over, this will go down, that is 3 times V phase times 2 pi F. Equivalent. Remember the IC we have got the total current, the power bank will consume, that is 38.74 amps divided by 3 times 400 times 2 times 22 over 7 times 50 hertz. And now let's see the value of C. Let's do calculator. Now the value of C, that's 38.74 amps divided by 3 times 400 times 2 times 50, which is equal to 10.27 microfarad farad. This is the capacitance per phase. The capacitor to be prepared per phase, which is equal to 10.27 microfarad. So this is the result. And then remember, for this configuration, these are put in parallel. Every phase it must occupy with a 10.27 microfarad capacitor. For our power factor to rise from 0.7 lagging to 0.9 lagging. So, my dear friend, this is the beginning of our sessions, but let's do what I had. Now, during this day, during my practice, I decided to share you this content about the power factor improvement, so that it can guide you and help you to do such kind of design. But for other time, I will give you an alternative way where you can use, no longer need the current, you can use the KVA within the tangent, so that it can be easier for you as alternative way. For another session, we will continue in power factor improvement, but we are gonna use the apparent power, the reactive power within the tangent, so that it can be easier for you. It will be very short, but for this is more somehow interesting due to the trigonometry applied. Thank you for today.